Hi everyone, thank you for joining me today. I'll be sharing what I'm calling a shared predictive framework for motor control and beat-based timing. The jumping off point is the observation that when we listen to something that induces the sense of a beat and we maintain that sense of the beat in our brains, in fMRI we see consistent activation in a couple of regions. One is a cortical area called the supplementary motor area, and one's a subcortical region called the basal ganglia, especially the putamen subregion. Both of these are considered motor areas in that they are consistently involved in coordinating and initiating movements. We also see them activated by continuing a beat by tapping. And I want to raise the question, how should we conceptualize the role of these motor areas in non-motor beat-based timekeeping? So I'm going to start by sharing some observations in supplementary motor area from monkey neurophysiology. When monkeys make cyclic actions, in this case turning a crank, if we record the firing rates of many neurons in SMA, we graph those firing rates in a high-dimensional space, and we use some dimensionality reduction techniques to boil them down to 3 dimensions. We see these firing rates making loops in the space, one loop corresponding to every turn of the crank, as if they are representing the phase of that cyclical action in real time. This also happens when monkeys do a synchronization continuation task and tap along with a periodic stimulus. And in this case, that loop represents the whole cycle of their action, including a part where they're just hovering their finger above the tap pad. So it's really an abstract representation, not a specifically motor representation of the progress through that cyclic action. In the same synchronization continuation task, it's been observed that populations of neurons in SMA initially lock to the cues that are pacing the monkey's tapping, and then over time, fewer of them lock to the pacing cues and more lock to the actual cycle of the action. So it seems that these neurons are both representing the phase of the cycle of cues, but also then representing the phase of the cycle of movement. So to highlight some of the tensions underlying this data, in humans it seems that the supplementary motor area is involved in both guiding movement, but also involved in passive entrainment to sound. And in monkeys, SMA neurons seem to represent the phase of motor output, but also represent the phase of cycle of auditory cues. I want to raise the question whether we can unify those different functions as parts of the same elephant, as it were, and suggest that the answer is yes, drawing on ideas in predictive processing and active inference that I'll outline now. The predictive processing framework characterizes cortical activity as representing beliefs about what's going on in the world around you. These beliefs are informed by top-down predictions or expectations of what's probably happening, and they produce their own predictions about what you should be experiencing that are sent down the cortical hierarchy. When these predictions are in error, error signals are then sent up the cortical hierarchy, where they serve to continuously update those representations to make them more accurate. Active inference extends these ideas to describe motor control by characterizing what we call motor commands as their own type of top-down predictions, describing what we expect to proprioceptively experience. When motor neurons receive these predictions, they cause us to move, minimizing the error between our proprioceptive predictions and our actual proprioceptive experience. What's exciting and weird about this idea is that motor cortical areas can now be doing 2 jobs at once, describing what the body is doing as accurately as possible and making predictions based on that, but also actually controlling the body to make those predictions accurate. Applying these ideas to SMA, we hypothesize that during cyclic movement, the supplementary motor activity is representing an estimate of the phase of our movement. The estimated phase advances steadily, because that's what we generally expect the phase of a cycle to do. Top-down signaling from SMA informs phase-based predictions about what we're going to experience in our bodies over the course of the cycle, and our body moves to make those predictions true. But SMA also informs phase-based predictions about what we're going to hear over the course of the cycle, in line with observations that it's involved in predicting self-generated sound. Errors in the timing of phase-based predictions, including predicted sound timing, are passed back up the cortical hierarchy, as described by the predictive processing account, and used to update the representation of cycle phase to align better with what's actually happening. So here's an example of how that might play out if you're just doing steady, unpaced, isochronous tapping. The SMA would represent the fact that we are at the point in that cycle where there should be a tap. It would predict towards these motor areas that we should experience a finger tap now. That prediction would contribute to lowering your finger and actually doing the tap. but if we weren't experiencing an impact yet, the prediction error would then serve to update our sense of where we are in the tap cycle. Similarly, SMA would predict towards auditory areas that we should be hearing a tap soon, and if we don't hear a tap right away, the prediction error from the auditory pathways would also serve to update the inference about the cycle of the phase that we're at in SMA. If we're in training to a set of isochronous cues, then the only difference is that SMA would be predicting that we should hear a tap or a click at a particular point, and errors in those predictions would then serve to update that sense of phase. And now if we're just covertly listening to a drum track, SMA would be making the same kinds of inferences about the phase of the cycle of the rhythm that we're listening to, would be predicting what things we should hear at what points in phase, and errors in those predictions would update the tracking of the phase in the supplementary motor area. In this case, we'd have no particular expectations for our body during that time, so we could be doing this all covertly, but tracking the phase of that sensory cycle in the same way. Now, all of this is appropriate for inferring the phase of a cycle if we already know the period of the cycle and what to expect at every phase. But in fact, we're very flexible about our rhythmic expectations with respect to tempo, with respect to the pattern of subdivisions between beats, and with respect to metrical groupings over longer timescales. All of this requires us to make rapid modifications to what we temporally expect based on what we've just heard. So what's the brain basis of this? Well, I want to suggest that this is now the role of the basal ganglia and the putamen that get activated by covert beat-based rhythms. Classically speaking, the basal ganglia is understood to take cortical input and along this direct pathway through globus pallidus and thalamus, select a motion plan by disinhibiting certain areas of motor-related cortex. But the perspective from the active inference view is that the direct pathway is integrating context in order to determine proprioceptive expectations. In other words, what to expect your body to do given certain context, including the task and your goals. And it's been suggested that the basal ganglia also may be disinhibiting areas of cortex representing what to expect along other sensory streams, what to expect in the immediate future, for instance, in audition. Here's an illustration of our hypothesized role of the basal ganglia in rhythmic expectation. Based on context, which can include recent listening history and also goals or intentions, it can establish an expected period for the next cycle of action or sound by disinhibiting certain populations in the supplementary motor area. Also, through disinhibition, it can establish an expected pattern of movement over the course of the next cycle, and establish an expected pattern of sound over the course of the next cycle. And this has a certain explanatory power for some phenomenology of Parkinson's disease. So when we lose that basal ganglia input, we should see difficulty selecting movement, which of course is a main symptom of Parkinson's, but also a lack of flexibility in tempo and specific rhythmic expectations, which has been observed in several publications. And in this picture, we also see a possible explanation for the incredible power of cyclic auditory cues to rehabilitate gait in Parkinson's disease. We understand those as possibly informing the estimate of phase of the step cycle in supplementary motor area, which can then be used to guide the time course of movement. An important data point to consider here is that giving someone auditory feedback from their own steps is actually even more effective than a metronome in training gait in Parkinson's, suggesting that we really can start to understand this as part of the process of controlling one's own movement based on its auditory consequences. Much of this presentation has been based on my recent work with Patel on the role of the motor system in beat-based timing. You can read more about that in our recent Trends in Cognitive Sciences paper. I've also been working on a mathematical model that looks at rhythm tracking in the framework of predictive coding in Bayesian inference, and that's in press at PLOS Bio, but also available on bioRxiv. Finally, I'm on my way to start at McMaster University as a faculty member in fall of 2022, and I'll be looking for graduate students. So if you know people who are interested in this kind of thinking or modeling, please drop me a line.